Ever wondered how AI can fix broken audio? Like filling in a missing note in a song or restoring a distorted voice recording. Today, we're diving into a cutting-edge technique called audio inpainting, where machines learn to reconstruct missing parts of sound using a mix of smart compression and diffusion models. Let's break it down. First, imagine you have a song with a gap, maybe a sudden silence or a corrupted section. Traditional methods might struggle to guess what belongs there. But this new approach uses something called WavTokenizer, a tool that converts audio into a sequence of simple tokens, like a codebook of sound snippets. Think of it as turning a complex melody into a series of building blocks. These tokens are easy for AI to work with, especially when paired with a discrete diffusion model, DDM. So how does the DDM work? Picture a movie being slowly blurred. The DDM learns to reverse that process, starting from the blurry version and gradually sharpening it back into focus. In audio terms, the model denoises the token sequence, filling in missing parts based on the surrounding context. But here's the trick. Instead of working directly on raw sound waves, which are messy and hard to model, the AI operates on these simplified tokens. This makes training faster and more stable. The magic happens during training. The model is shown audio with random gaps and learns to predict what's missing. It uses something called a score function, a kind of mathematical guide that tells the AI, how likely is this token to fit here? By tweaking this function, the model gets better at reconstructing realistic sounds. Now, when it's time to test the model, researchers use metrics like Frachet audio distance, FAD, and log spectral distance, LSD, to measure how close the restored audio is to the original. Lower scores mean better results, like a puzzle piece that fits perfectly. In experiments, this method outperformed older techniques, even handling long gaps of up to 300 milliseconds with impressive accuracy. The real-world impact. Imagine restoring old recordings, fixing audio in movies, or even creating music that fills in missing sections seamlessly. This isn't just about fixing errors, it's about expanding what AI can do with sound. So what's next? This approach opens the door to more robust audio restoration tools, maybe even for podcasts, movies, or live performances. And who knows? Maybe one day, your favorite song's missing chorus will be magically reconstructed with just a few clicks. Thanks for watching. If you want to hear the audio examples, check the link in the description. And don't forget to like, subscribe, and hit that bell for more deep dives into the science behind the tech. Until next time, keep listening, keep exploring. Hey everyone, welcome back. Let's dive into a fascinating area of modern AI that builds on the ideas we just explored with Markov chains. Imagine a world where machines can generate realistic images, restore broken audio, or even compose music without being explicitly programmed. How do they do that? The answer lies in diffusion models, a powerful class of algorithms that's taking AI by storm. So what's a diffusion model? Think of it like a digital, reverse engineering process. These models start with a noisy, scrambled version of data, say a blurry image or a corrupted audio clip, and gradually unscrambles it, step by step, to reveal a clear, realistic output. It's like watching a video in reverse. First you see a mess, then the details emerge. But how does this work? Let's break it down. Diffusion models are inspired by physical processes, like how ink spreads in water. They use a stochastic process, essentially a system that evolves over time with some randomness, to add noise to data in a controlled way. Then the model learns to undo that noise, effectively denoising the data. This is where the connection to Markov chains comes in. Both involve transitions between states over time, but diffusion models take this idea into the realm of machine learning. Now, why is this so exciting? Let's look at some real-world applications. In 2021, researchers showed that diffusion models can outperform traditional GANs, those famous image-generating networks, at creating hyperrealistic images. And in audio, models like DiffWave, Reference, use diffusion to synthesize music and speech with astonishing clarity. Imagine fixing a damaged old song or filling in missing parts of a recording. Diffusion models are making that possible. But it's not just about images and audio. These techniques are also revolutionizing language processing. For example, the BERT model, Reference, uses similar principles to understand context in text, while newer diffusion language models, Reference, are pushing the boundaries of text generation. It's like giving machines a deeper, more nuanced understanding of how data evolves over time. What makes diffusion models so versatile? The key lies in their ability to model complex probability distributions. Unlike traditional generative models that rely on direct optimization, diffusion models iteratively refine their output through a series of denoising steps. This approach allows them to capture intricate patterns in data, whether it's the texture of a painting, the rhythm of a song, or the nuance of human speech. But how do they handle high-dimensional data like audio? Let's get technical. Audio signals are inherently sequential, with time-dependent relationships between samples. Diffusion models tackle this by first transforming the audio into a compressed representation, like the tokenized format we discussed earlier. This reduces computational complexity while preserving critical features. The model then applies diffusion to this compressed space, gradually reconstructing the original signal with remarkable fidelity. This is where the discrete aspect of the model becomes crucial. Traditional diffusion models operate on continuous data, but the discrete version used here works with quantized tokens. This not only speeds up training, but also allows the model to learn semantic structures, like musical motifs or phonetic patterns, that are essential for realistic reconstruction. The implications are staggering. From restoring historical recordings to enabling real-time audio editing, this technology is reshaping how we interact with sound. And as research progresses, we can expect even more applications in fields like virtual reality, assistive technologies, and creative arts. So next time you hear a song with a glitch, remember, behind the scenes, a blend of tokenization, diffusion models, and smart algorithms is working to make it sound perfect again. Thanks for watching, stay curious, and let's keep exploring the future of audio tech.